Okay, Chemistry 3101. We're going to start a little bit of final exam review in kind of a weird spot, okay? It's kind of a strange spot to start review, but I want to talk about naming alcohols. Now, this is something that isn't covered in depth until Organic Chemistry 2. However, they expect you to take the rationale of naming something like an alkene or an alkyne and be able to apply that to naming an alcohol. And don't get stressed out about it, because when I show you the rules that are on this page, you're going to see how all the rules that apply to naming alkenes and alkynes apply to naming alcohols. The only difference is, like, let's say you were naming an alkene, right? How does your name always end? It ends with "ene," right? But when we're naming an alcohol, the difference is this: the end of the name is going to end with "all." That is it. So again, if you can name an alkane, an alkyne, or an alkene, you can name an alcohol, my friend, okay? It even says here, alcohols are named using the same procedures that we even used in chapter 4 for naming an alkane, just with a couple of modifications. So, first rule, we find the longest chain, the parent chain, but it's got to include the alcohol functional group, the same way we did with alkenes and alkynes. That's about it. The next thing, you identify and name the substituents. Is it a is it a 2-methyl, 3-ethyl, whatever, okay? You give a locant. Remember, that's just a fancy word for a number, right? A locant just means a number, and a prefix like di, tri, here, etc., okay, to each substituent. So then, here's the important one. Give the carbon with the hydroxyl group the lowest number possible. And then you list the substituents before the parent in alphabetical order. You ignore prefixes except iso. What were the other two? Cyclo. Cyclo. I can't write this morning. And neo. And there you go. And then you can put the hydroxyl, the OH locant, just before the parent name or before the suffix. So what does this last rule mean? Let me show you an example. So let's say you had something like this. Let me use my black pen. So let's say you had 6 carbons in a row. 1, 2, 3, 4, 5, 6. Okay. And let's say you had your hydroxyl group here. Okay. There's your alcohol functional group. You could call this 2-hexanol, or you could call it hexan 2-all. And again, the reason I bring this up is because on the final exam, sometimes, and you'll see this in organic too, they'll expect you to name compounds that you've never really looked at, but they want you to apply the knowledge that you've already learned in the class. So here's some examples, right? Let's say you have pentane. Well, if you have a hydroxyl group, it's not ane, it's all, right? It's pentanol. And here, the hydroxyl group is on the first carbon of the 5-carbon chain. You see me numbering it here. So this would actually be 1-pentanol. Here you see the longest chain here has 8 carbons, so it's octane. So this would be 4-methyl-octane. I won't write that in. But here, remember, the longest chain has to include the hydroxyl the same way it did with an alkene. So this is a 1-hexanol, right? We have 1, 2, 3, 4, 5, 6. So this is 1-hexanol. So this would be what? 3, and this is a propyl group right here. So this would be 3 propyl, 1-hexanol, or you could call it 3-propyl hexan 1-all. Either one is totally fine. And so here's what you're going to see on the final exam: is there's a question where they ask you to name a compound that has 2 functional groups in it. Okay, it's got an alkene and an alcohol in the same compound. Okay, now you're not asked to pull the name out of thin air because they give you the possible answers, right? Because it's a multiple choice exam. So you just have to be able to recognize which one is the correct answer. But if you have these 2 functional groups, namely an alcohol and an alkene in the same compound, you might ask yourself, well, how would you name this compound? Is it an alcohol or is it an alkene? And the answer is based off of something called the order of precedence of functional groups. And the idea is that the alcohol takes precedence. And so we would call this compound, you would not say this is an alkene, you would say this is an alcohol, and then it has an alkene in it, okay? So generally speaking, if you have a functional group that has an oxygen in it, it takes precedence over a functional group like an alkene or an alkyne that only contains carbon and hydrogen. So how would you name a compound like this one on the left? You see the one on the right is incorrect because, again, the hydroxyl gets precedence, so we want to give it the lowest number. So there's a total of 7 carbons in here, so this is some kind of hexan 2-all, right? But the way we label the alkene is we say it's a, let me see if I can squeeze it in here, 6-hexene. Okay, you see this letter E here? That is tied to this number 6. So it's a 6-hexene, and then we put 2-ol. So now you can see why in Chemistry 3101 you learn this method where you can put the locant either before the parent or before the suffix. Okay, so this is some kind of 6-hexene 2-ol. And then we have our 3 methyl groups. We have 5,5,6 trimethyl. So let's see if I can squeeze that in here. So we'll say 5,5,6 trimethyl. All right, there we go. So 5,5,6 trimethyl, 6-hexene 2-ol. So that's how you would name a bifunctional compound like this. And don't stress about it too much. There's only one question on the exam like that. But again, now you know how to do it. And we always give the alcohol precedence. So if we go over to the ACS study guide, so let me just find it here. Give me a second. It's right here. Okay, you'll see at the very beginning there's a question like that. It's question 7. Okay, so we have this compound, and the way that it's put in the box here, I think nothing is easy in organic chemistry, but I'd say it's relatively straightforward for my students to see where the longest chain is. Right, you can see it's 1, 2, 3, 4, 5, 6, 7. 7. So we know this is some kind of 2-hexanol, or sorry, heptanol. So it's some kind of heptane 2-ol. So we can cross this one off because it says it's a hexanol. Well, that's not true. And then this one here, they numbered it incorrectly, right? So they gave the locant for the hydroxyl, the number 6, which is incorrect. That would mean they had started numbering here, which would be incorrect, okay? So we can cross that one off too. So now it's a battle between these two, C and D, and you see how all of this is identical, right? The 5-methyl-4-heptene 2-ol is the exact same. And again, you can see they put the locant for the double bond is 4, and the locant for the hydroxyl is 2. So that's all good. So then the next question is this an E compound or is this a Z compound? Could anybody answer that? And it's not a trick question. ACS doesn't have trick questions. This is just, yeah, thanks, Jenny. Absolutely. It's a Z compound. So Jenny says, well, if you look at the green carbon, it's going to be, I'll use my green pen, I guess. It's going to be this group that takes precedence. And then she said, okay, well, if you look at this carbon over here, number 4, you can see it's this group that takes precedence. So she's absolutely right. This is a Z compound. And there you go. Now, if you're sitting there and wondering, does that mean a lot of these questions I can kind of solve by process of elimination? I would say yes. Many of them can be solved by process of elimination. But give me a thumbs up if you're even with me like part of the way on naming a compound that has an alkene and an alcohol. Okay, cool. All right, so now you know how to do that. I want to back up into something that's a little more, question number 3. Actually, you know what? Let's just try this one for fun. Okay, I know, again, I just showed you these rules quickly, but do you guys think you could name this alcohol or find the right name? Could I give you a second to look at this? Okay, you can see the longest chain. I'll help you a little bit. I mean, you probably don't need my help one bit. But could anybody tell me which one of these would be the right answer? A, B, C, or D? And I know it's kind of quick, so just take your time. Yeah, absolutely. Raul, yeah, absolutely. Right? Totally. You're 100% correct. So what Raul is saying is he said, well, should I start at this carbon that I have the blue question mark, or should I start numbering at this carbon that I have the red question mark? And the answer is the one with the red question mark, right? Because then you're going to give the hydroxyl the lowest possible number, right? 1, 2, 3, 4, 5, 6. If you had started numbering over here, it'd be 1, 2, 3, 4, right? And this is an alcohol. And so this is some kind of 3-hexanol. So that is just based off of that, you'd get the right answer, right? But then you see you have the 5,5-dimethyl. You have a methyl group here and a methyl group here. So absolutely, absolutely. Okay, let's move on to something that's near and dear to all of our hearts, and that's naming alkenes. Okay, so question 3 is a great question. So it just says, which compound is E12-dichloro-2-pentene? I'd say there's a couple of ways you could solve this. you could either go through every single answer and then just say, okay, does this look reasonable? Something that I like to do sometimes is draw the compound myself and then kind of compare my answer to the answers that are here. So if somebody asked me to draw this compound, I'd say, okay, it's a 2-pentene, and so I'd say I've got a double bond, so 1, 2, 3, 4, 5, and then I've got a 1-chloro and so what is it? 1,2-dichloro, and then it's an E compound, and you can see that this is the most important group. And so yeah, what I've drawn is the right compound. So based off of that, you could kind of go through these and just kind of figure out which one is the correct one. Does anybody recognize? Well, if we look at B, you can see that B goes 1, 2, so it's a 1,2-dichloro. But if you look at these two, this is the highest. Actually, did I draw the correct way? No, I didn't. Sorry. I drew it incorrectly. Let's try it again. So this would be the highest priority group, and then this would be the highest priority group, wouldn't it? So that would be a Z compound, what I drew. So let me just fix it. There we go. There we go. That's the right compound here. So if I look at B, now I can see what was wrong with B. If you look at B, you can see that this is a Z compound, so this is not right. If you look at C, it's an E compound, but you have 1, 2, 3, so your double bond, so this is a 3-pentene, so that's not right. If you look at number 4, you can see that this is a Z compound, so that one's not right. So then if you go to A, take a look at A, so let me fix that up. All right, so we have 1, 2, 3, 4, 5. You can see that this is an E compound because the chlorine takes precedence and the ethyl group takes precedence. So this is an E compound. You have a chlorine at carbons 1 and 2. So there you go. You have your double bond at carbon 2. So A would be the correct compound. So this is the correct compound right here. All right. Give me a thumbs up if you follow me on that one. Everybody with me on that one? E and Z? Yeah? Okay. Can I just tell you what I think the trickiest part is on this one? And I've taught this class for a long time. What I think is the most challenging part about this problem is this. Ooh, where's my eraser? Okay, and I know that some of you, I might be going too slow, but just bear with me, okay? I think the most difficult part is looking at these two groups on this carbon, right? Sometimes students will just automatically say, well, this group takes precedence because it's bigger, right? It's got more atoms. It's going to take precedence over the chlorine. Well, that's not true because you're actually comparing the atom that's directly attached, right? We have a carbon and a chlorine. Well, a chlorine has a higher atomic number, right? So it takes precedence. And then I think it's usually relatively straightforward for my students to say, well, this group is going to take precedence. So this is an E compound. So remember, when we're using E and Z designation, it follows the same pattern or rules as the Kahn-Ingold prelog. So we go by the first atom that it's attached to. Okay. So we've got number 1 done. We did number 3. Let's try number 5. I noticed that I scribbled all over this, but anyhow, this is a good question. Number 5, it says, which is the structure of Z? So zusammen, 3,5-dimethyl-3-nonene. So again, you could try drawing the compound yourself, but I think a good way to try this is maybe look to see which compounds are Z and which compounds are E. So if we look at A, we start with A, you can see that this compound can't be E or Z because you've got 2 methyl groups on this carbon, so not E or Z, so it doesn't apply to that one, so it can't be that, so we'll just scratch that one off. If you look at this one, you can see I already scribbled E on here, but let's just see if I was right. If we look at this carbon in red, the ethyl group is going to take precedence. If we look at this carbon in blue, you can see that all of this group is going to take precedence, right? There's a hydrogen down here. So this is an E compound for sure. So this definitely can't be an answer. If you look at C, if we look at this carbon in blue, it's the ethyl group that's going to take precedence. If you look at this carbon in red, it's all of this that's going to take precedence. So this is a Z compound. So we can put a Z by that. So far, so good. And then if you look at the last one quickly, you can see that the ethyl group is going to take precedence. And if you look at this carbon, you can see that this group, so this is an E compound. So C had better be the right answer. Otherwise, we're in serious trouble. But if we number the carbons in C, I'll use my blue pen. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that looks good. It's a 3 nonene, and then we have methyl groups at carbons 3 and 5. So yeah, it looks good to me. It's the Z35 dimethyl 3 nonene. All right. Okay. And like I said, I'm not going to ask you for a thumbs up after every question, but if there's a concept you're missing or something that isn't unclear to you, don't hesitate to stop me. So I'll just put this other bug in your ear. And I told you this earlier on, but the ACS study guide, keep in mind that it mixes both chemistry 3101 and 3111. They're all jumbled in together. So don't worry about naming, something like this. We didn't talk about phenol nomenclature. We didn't talk about naming aromatic compounds at all. So don't stress about that. We didn't talk about naming ketones. So don't worry about that. We certainly didn't talk about benzamide, right? That wasn't part of the content of this class. So there you go. There you go. So we've covered some nomenclature questions. All right, let's take a look at question number 3 here. So we're moving into the next section, which is structure, hybridization, and resonance and aromaticity. So quite a few things covered here, but I like question 3. Why, and I'm not trying to be crude or sounding mean or anything or intimidating, but this is a question that could have been asked in General Chemistry 1, okay? So why? Because it's just a Lewis structure question, okay? So you got to be on the spot on Lewis structures. Now you can see here it says, which is an acceptable Lewis structure for diazomethane? Well, obviously there's only one correct answer here, right? 3 of them are wrong and 1 of them is right. But if we just look at the structure of all of them, you can see the formula for diazomethane is CH2N2, okay? That must be the formula, okay? The formula is the same. So even if you didn't know the structure of diazomethane, they've given you that much. Now, my question to you is, could anybody tally up the total number of valence electrons for diazomethane? So, right, for Lewis structures, we always want the total number of valence electrons, TVE. Could anybody tally that up and tell me how many total valence electrons there are in diazomethane? Okay, if you're unsure, so just remember carbon has 4 valence electrons, hydrogen has 1, and nitrogen has 5. So that would mean 4 plus 1 times 2 plus 5 times 2. So that would give me a total of 16 valence electrons, right? This is something that you still have to be able to do. If you remember way back in General Chemistry 1, you would look at something like CO2 or titanium tetrachloride or something like that, right? And then you'd have to tally up the total number of valence electrons. So this is still a thing. All right, so 16 valence electrons. Now, in the time that I've been rambling on here, did anybody notice anything here that's just totally wrong in any of these? Is there anything? You're right, Jenny. What's the sin that's been the transgression that was committed in A? Could you tell me quickly? Just type it in the chat. Because you're totally right. There's a big problem in A. Yeah, exactly. Right. So Jenny said there's too many valence electrons around this nitrogen. Okay. There's 10 valence electrons. So, right. Nitrogen is in the second period. It can't exceed an octet. So that's a big time no. Also, if you tally up the total number, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that looks right. Okay, they just put way too many electrons around the nitrogen there, so that's a big time problem. What else? Does anybody else see anything that's particularly egregious here? I'd say that if you look at C and tally up the total number of valence, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this one only has 14 valence electrons, so that's a big no-no. So now we've eliminated 2 of them. If we come to B, let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that looks good. That's 16 valence electrons. Okay, and I don't see any other violations in B. But hold the phone. Let's take a look at D. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That looks like a problem, doesn't it? Okay, we have too many valence electrons in here. Okay, and you can also see that this nitrogen, I just noticed, this nitrogen is exceeding the octet rule. Okay, so you know what we'll write here? We'll put octet rule. octet. Here, let me use a darker font here, rule. And then this one here is also disobeying the octet rule. And C doesn't even have enough electrons. And so B would be the best choice here for diazomethane. Yeah, thanks, Isaac. You're absolutely right. Yeah. So again, we kind of solved that one by process of elimination, but that looks totally reasonable for me. Diazomethane is a really cool molecule. It's used to do something called diazotize, or anyhow, doesn't matter. But it's also kind of explosive, so kind of something kind of interesting there. Anyhow, let's move on. What was the next one I had on the hit parade here? Was question number 5, I think I wanted to look at. Yeah, question number 5. Let's look at question number 5. Okay, it says here, which formula is equivalent to the condensed formula that's shown here? This is the kind of question that the vast majority of my students are going to get correct, okay? If you just look at this condensed formula, if I was to ask you to draw a bond line structure of that, where I would start would be with this carbon, right? If I highlight this carbon in blue, so if I have this carbon, then it's got 3 methyl groups, okay? So if I circle these in red, it's got 1, 2, 3 methyl groups. Then it has 2 methylenes, all right? So you have 1, 2, and then it has a methyl, right? A methyl on the end, so 1, 2, 3. So that's the compound. So if I draw the bond line structure, it's just so 1, 2, 3, 4, 5. So it's 1, 2, 3, 4, 5. There you go. So it's 2,2-dimethyl pentane. Okay, and then you look at the structures and you see that it's D. But one thing, does anybody notice a major problem with D, or with B? Sorry, does anybody notice a major problem with B, that it's like almost burns your eyes kind of thing? Yeah, absolutely. Okay, exactly. Right. Too many bonds to the carbon. So that's a huge no-no. Also, we generally speaking don't put rings in condensed structures. So that's something that we haven't even looked at. Okay, so we generally don't do that. And so clearly you can see that this one is the correct answer. Okay, cool. Let's move on to number 6. Number 6 is one of those questions that never goes away in organic chemistry. Okay, I didn't make a note, but this pyridine, we either looked at it in chapter 1 or chapter 2. It might have been chapter 1. Yeah, it might be chapter 1, because we talked about hybridization, right? Remember, that was a big topic. And hybridization, that's sp2, sp3, right? In general chemistry, you looked at sp3d, sp3d2. Okay, we don't even look at those in this class. But if you go back to chapter 1, you could even go back and watch my videos probably, and you'll remember that there was a part where I said, I want you to memorize, okay, what orbital, or what kind of orbital the lone pair of electrons is in on the nitrogen of pyridine. Okay, so this molecule here, this is pyridine. Okay, so it's an aromatic compound, but what type of orbital are those electrons in? Well, here's the way you figure it out. Okay, notice that the nitrogen has a double bond on it. Okay, how do you make a pi bond? The way that a pi bond is made, okay, and this is just review, right? That's what we're doing, is the side-to-side overlap of 2 p orbitals, like this. We have a p orbital and a p orbital. So that tells me that there is a p orbital on the nitrogen for sure, but it's being used to make this pi bond. Okay? Now, what is the steric number of that nitrogen? It's 3, right? So that means that it's sp2 hybridized, but the p orbital is being used for the pi bond. So that means that the lone pair on the nitrogen is actually perpendicular to the plane, and is actually an sp2 hybrid orbital. So here we go. It's in an sp2 hybrid orbital. Okay. If you don't believe me, okay, I don't know if we have time to do this, and I don't really need to show you because you guys know this already. Anyhow, but if you go back to our lecture notes, very end, okay, where was it? Now I won't be able to find it now that I've pontificated about it, right? Like, Mr. Dion, what were you talking about? but I thought it was in here. I don't remember where it was. It's in here somewhere that we talked about pyridine. Darn it. I'm really off in left field now that I got the camera on. Anyhow, how do I get out of here? There we go. Anyhow, I'll go back and look to see exactly where it was in the slides, but we did cover it in class. Does anybody give me a thumbs up if you remember talking about it? Because we did go over that. Does anybody remember chatting about pyridine? Oh, okay. All right. I'll find it in the notes. So I'll make a note here and I'll post it in an announcement if you want to go back and check. So pyridine. All right. Okay, so let's see here. Let's try question number 7. Question number 7. This is the kind of question that I would expect when I run the numbers. 95% of my students are going to nail this. So question number 7, it just says, what are the hybridizations of the atoms marked 1, 2, 3, and 4? I'll give you a second to look at it. All right, anybody have an answer for this one? So if I look at number 1, right, atom number 1, its hybridization is going to be sp2. If I look at atom number 2, its hybridization is going to be sp3. If I look at atom number 3, right, Jenny, it's going to be sp2, and number 4 is going to be sp3. Exactly. Thanks, Jenny. sp2, sp3, sp2, sp3. Right? There you go. I just found it, by the way, BTW. So it's in chapter 2. Okay, if you go down to the end of chapter 2, it's right here. Okay, so when we talked about localized and delocalized lone pairs, so this is pyridine. All right, so this is pyridine. You can see that we talked about it in class right here, pyridine, and the lone pair in pyridine is in an sp2 hybridized orbital. So it's section 2.12 if you want to go back and take a look at that. All right, let's go back to the study guide. I think my chapter's mixed up here. Okay, so we've got that one down. So just a little bit about hybridization. So you should know how to identify the hybridization of a carbon or a nitrogen or an oxygen. Okay, so make sure you're able to do that. And let's take a look at, hey, who wants to talk about some chapter 10 chemistry? Okay, yes, that is my finger because I was trying to keep the book open. So chapter 10, this is near and dear to us. We just covered it last week. For which free radical can the most resonance forms be written to show delocalization? Could anybody tell me which one of these you could draw the most resonance forms? Exactly. Thanks, Raul. You're absolutely correct. Is D. Right. This one is This one's doubly benzylic. We'll put benzylic times 2. This one is benzylic as well. Okay. This one is vinylic. Vinylic. So that's just a huge no-no. This is so unstable. And then this one here is primary. Okay. So there's no resonance forms that you can draw for this. Right. For the benzylic one, you could start, with something like this. Not very pretty. There we go. And you can start drawing resonance forms like this. But for this one, you've got way more resonance forms that you could draw. You could have a total of 7 resonance forms for this guy, and this one you'd only have a total of, not 5. You'd have a total of 4. Okay. Anyhow, you could try and draw these. Try to draw. We're not going to do it right now, but you could, take some time maybe and see if you could draw all the resonance forms for this. Okay. All right, let's move on to question number 11. Question 11. Okay, question number 11. Did we talk about resonance? Is the Pope Catholic? Yes, we talked about resonance quite a bit. Okay, so we talked about resonance a lot in this class. Okay, and it just is asking us out of these 4, which which two would be resonance forms, okay? I want to ask you about B first, because I feel like B is the lowest hanging fruit. Could anybody tell me, is B resonance forms? Are those two resonance forms in B, yes or no? And it's not me trying to fool you. Those are not resonance forms, are they? Right? Because one is trans and one is cis. Those are stereoisomers. That has nothing to do with resonance, okay? C is actually kind of an interesting one, and I'm going to go over this in detail, but these are not resonance forms. These are just two different carbocations, okay? So they're not resonance forms of each other, though, okay? Actually, what's happening here is that the ring is expanding. So this is a ring expansion, okay? And this goes back to the discussion we had before I started recording today. I asked you guys which kind of ring is preferred, and Raul said a 6-membered ring, and he's totally right, okay? And a 5-membered ring is below it. What about D? Would D be resonance forms? So in D, this one, you can see the hydroxyl and the phenyl are on opposite sides. So this is an E alkene, and this one, they're on the same side. So this is a Z alkene. So those aren't resonance forms either. It's actually A that have the two resonance forms, okay? But for this one, I would say that you kind of need, you would want to use your scratch paper to draw all of these, okay? So what we're going to do is we're going to move over to a piece of scratch paper right here, and we're going to try and draw all of the resonance forms here. So if we start out with this form, this is what they gave us first. So I'll just use bond line structure. Okay, there we go. So let's start with some curved arrows. So we could move the bond over here. Then we end up with something that looks like this, where we have the positive charge here. Okay, and then we can draw another resonance form. So we can move this double bond over here, and then we end up with something that looks like this. And what do you know? If this and this are the two structures that they had shown. So they left this one out, okay? But the two with the yellow line underneath them, they are resonance forms of each other. And so the answer is going to be A for that one, okay? So A, those are the two resonance forms. So if we go back to the study guide here, let me find it. It is, where was I? It's A, these two here. So you'd want to write all those out, or at least I would, okay? Now, what I want to do for a second is I want to show you this ring expansion, okay? So it's another form of rearrangement that you are expected to be able to think about as an organic chemistry student. And I had written something down about the ring expansion here that I wanted to share with you. So let me just switch gears here for a sec. And we'll go over to a blank document again. So if you're making notes, write this down. Okay, if you're making notes, just make a quick note of this with me. So we were talking, again, this morning before I started recording, we were talking about 5 versus 6-membered rings, and we said that 6 is more stable. Okay, in fact, 6-membered rings are the most preferred rings in all of organic chemistry. And so a mechanism I wanted to show you is this one here. So let's say you had this compound, and this is nothing scary for you guys. I mean, you've seen alkenes like this 1,000 times this semester, okay? Let's say I treated that with, come on, trying to make a nice parallel bond here, but let's say you treated this with H3O plus, okay? So you treat this with H3O plus. I'm gonna do a mechanism, so instead of just writing the condensed structure, I'm gonna put the whole structure like this. So what would happen would be a Markov-Nikov addition, right? So if we draw our first curved arrow, we're going to do our proton transfer, and we're going to draw the carbocation that results, okay? So the carbocation that we get would be this secondary carbocation, like that. Now, there's a proton, there's, yeah, there's a proton that is here, okay? And you might be tempted to say, well, I could get, you know, a shift like this, and that probably can happen. That's the thing about organic chemistry, is that we oftentimes end up with mixtures, okay? And so we would end up with a carbocation that is tertiary like that, okay? However, there's actually something else that can happen as well, and I want to show you. Okay, so if I redraw this carbocation like this, okay, there is another possibility for a rearrangement here, and it is that this bond can actually go over here. Okay, so think about it. There are two electrons in this bond. Okay, so if those two electrons go over here to this carbon that I have in red, and let's put this carbon in blue like that, then what's going to happen is the carbon in blue is not going to have a complete octet, but the carbon in red will have a complete octet, won't it? So if you draw the result of this red arrow that I just drew, now you're going to have a ring that has, let's count. I'll get my purple pen out here to be different. So we have 1, 2, 3, 4, 5, 6 atoms in the ring. So now if I draw that 1, 2, 3, 4, 5, 6, if I put the blue carbon here and the red carbon here like this, then I'm going to have a methyl group here and a methyl group here, but my positive charge is going to be on the blue carbon because now it doesn't have a complete octet. And so at this point, you end up with some, so this is going, if I compare this carbocation versus this carbocation, this one is going to be more stable because it's a 6-membered ring. And now water, right, which is the conjugate base of hydronium, can come in as my nucleophile and it can attack here. And then I'm going to end up with this intermediate, okay, this guy here, right? And we have our methyl group here. And then after a proton transfer, I'll just put proton transfer, you're going to end up with this tertiary alcohol, okay? There you go. So in organic chemistry, right, often, you saw this in chapter 7, oftentimes we get mixtures. So in this case, might we get a mixture? Yes, but the bottom line is that the carbocation in the circle at the bottom with the 6-membered ring is going to be more stable than the carbocation in the 5-membered ring, okay? And this is just a different type of rearrangement here. This is a rearrangement, and it's called a ring expansion. A ring expansion, okay? And it's something that the reason I bring it up so much is I've seen it brought up on ACS and MCAT and DAT exams, and they kind of just expect you to figure it out, but here's your instructor kind of telling you, they're expecting you to apply the knowledge of a 6-membered ring is more stable than a 5-membered ring. But I'd say, again, that this is possible and this is possible. It just happens to be that the 6-membered ring is more stable, and so it's going to be the preferred carbocation that you would form, okay? There you go. So a little bit about ring expansions. All right. So let's try something. Let's try question number 16 in that part about the aromaticity and resonance and hybridization. It was this one right here, okay? Carbocations, okay? There's a subject that we talked about quite a bit. And we were just talking about it in the previous example when I was showing you the ring expansion. So here we have 4 carbocations, and we're asked to determine which one is the most stable, okay? Can I ask you guys a question first? Are there any of these carbocations that look really unstable? I'm talking like you just look at it and just say, that would never happen. That is so unstable. There's one of them. I'll tell you right now. There's one that's really bad. It just wouldn't happen. One really unstable carbocation here. It's not C. C is okay because it's benzylic. B is primary. There's one that's even worse. It's D, okay? So remember what I told you is that if you have anything vinylic, that is, so if you ever draw, get a thicker pen here. If you draw a vinylic radical or a vinylic carbocation, and that would be the same thing if you have a double bond with right? Okay, so remember this, okay? Everything that I just drew is ugly, okay? None of these things are ever going to happen. You're not going to have vinylic radicals or vinylic carbocations. These are unstable, okay? It's a huge, huge red flag. So if you see a positive charge on a double bond like that, That is a big time no, not happening. Now, if we look at the other carbocations, you see that in A, that the carbocation is secondary, but it's also benzylic. Benzylic. Okay. Let's go back. So let's try it again. Okay. This one is secondary benzylic. This one here is just plain old primary. So you're right, that is unstable. But this one here is primary, but it's benzylic. Okay. But even worse than primary is vinylic. Vinylic is the worst of all of them. It's even worse than primary. But you're right to think that, yeah, B doesn't look very good and C doesn't look, D doesn't look very good. So now it's kind of a battle between secondary benzylic and primary benzylic. Well, I think we can all agree that secondary benzylic is going to be more stable, right? So secondary benzylic is the best, okay? So don't be fooled by looking at a carbocation that is primary benzylic. So remember what the benzylic position is. If you have an aromatic ring, okay, if you have an aromatic ring, the first position, this position here, is the benzylic position, okay? So if you have a carbocation there, you might think, oh, that's primary. He told me that's really unstable. Primary carbocations are unstable, but you can't compare this versus this. They're not even anywhere in the same realm, right? Because this one, I can draw a whole bunch of resonance forms for it, okay? So a primary benzylic isn't that unstable. It's more stable than a tertiary carbocation. All right, does that help? Little short Sparks Notes lesson on benzylic carbons, okay? They're not a bad thing. They're a good thing, okay, as far as carbocations are concerned. Okay, cool. Let's move on. Let's go into stereochemistry for a minute. Okay, I find that generally speaking, my students are really, really good at the Kahn-Ingold Prelog rules. So identifying molecules as being R or S, I find that students are usually very, very good at this. But this question, any of you could have, written this question, right? Just give my students 4 molecules and ask them 3 of them are S and 1 of them is R. Find the one that's R, okay? So if we start with A, we start with the hydroxyl is going to be number 1. This carbon is going to be number 2. This is going to be number 3. So we're going like this. The hydrogen is in the back, so this is an S molecule. If I look at B, I'll use blue for B. This is going to be number 1. This will be number 2. This will be number 3. So I'm going this way. The hydrogen is in the back, so this is also an S molecule. If I look at D, in D, the hydroxyl is number 1. The nitrile, this one here, that's going to be number 2. So number 2, the methyl is 3. The hydrogen is in the back, so this is going counterclockwise. So this is also an S molecule. I should have used red for all of these, huh? Anyhow, but then if we look at C, you can see the lowest priority group in this case is a methyl group. Okay, it's not a hydrogen in this case. That's going to be group number 4. This will be 1, this will be 2, and this will be 3. So in this case, we're going clockwise, and so this would be an R molecule. Give me a thumbs up. Any questions about the Kahn-Ingold Prelog rules and how we figured that out? Okay, good. Let's try number 2, because number 2 is trickier. And I find that ACS loves to ask more than one question on the same question. Does everybody know what C6H5 means? Okay, C6H5 is the same thing as a phenyl, which is the same thing as this. Okay, it's just an aromatic ring as a substituent. That's what C6H5 stands for. Okay, so we're asked to determine the configuration of the 2 carbons here. So I'll put this carbon in blue and then the carbon in red. So if we start with the carbon in blue, the hydrogen is coming out towards us. And so whatever we find, we're going to have to reverse it. Is everybody aware of what D is? D, does anybody know what D stands for? There's no element D on the periodic table. D is deuterium. Deuterium, which is the same thing as hydrogen 2, okay? So hydrogen 2 has 1 neutron in the nucleus. And so deuterium is going to take precedence over a hydrogen, Okay, and we see deuterium used every once in a while in multiple choice exams because it helps the test giver to be able to test the student on whether it's syn addition, anti-addition, that kind of thing. So deuterium, it's got a neutron in the nucleus, whereas a proton doesn't. So deuterium takes precedence over a hydrogen atom. So if we look at the carbon in blue, we'd start with, so this one has a carbon, right? And this one is a deuterium, this one's a hydrogen. So this is going to be group number 3, this is group number 4. But this one here, this one is attached to carbon, it would be attached to carbon, 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 whereas the carbon in red is attached to sulfur, oxygen, carbon. So that means the carbon in red is going to take precedence. So this is going to be 1, this will be 2. So we're going 1, 2, 3, like this, which is counterclockwise. So that would be S, but remember the proton is coming up towards us, so we reverse it. So this would be R. So we know the left carbon is R, so we can cross off B and C. Now if we go to the carbon on the right, the red one, red for right, okay? This one, if we put the order of precedence, the sulfur is first, the oxygen is second, and then all of this spinach is going to take precedence over the methyl group. So we have 3 for all of this. The methyl group's in the back, so we're going 1, 2, 3. So that's clockwise, and so this one is R as well. And so A must be the answer, and there we have it. So a little bit of Kahn-Ingold pre-log rules there. All right. Any questions about Kahn-Ingold pre-log rules, which is just the SATSI way of saying designating a stereocenter as R or S? Okay, well, let's talk about some symmetry here for a sec. And let's take a look at question number 5. It just says, which of these molecules are meso? Okay, so we're looking for a meso compound. Okay, can anybody identify any of these compounds as meso? Well, before we do, let's figure out what the definition of meso is. So remember, in meso, we have to have stereocenters, right? Meso compounds is usually 2 stereocenters, but a plane of symmetry. So if I look at compound number 1, are there any stereocenters in compound number 1? Are there any stereocenters in compound number 1? Is it yes or no? Right, Jenny? None. There's no stereocenters in here. So that can't be a meso compound, right? You might say, oh, there's symmetry in there. It's meso. No, just because it's symmetry, there's symmetry in cyclohexane, but that's not a meso compound, right? So this is not a meso compound. So we can scratch off A and D right away. We can get rid of those, okay? Now, if we look at 2 and 3, you can see that one of them is cis 1,2-dichlorocyclopropane, and the other one is trans 1,2-dichlorocyclopropane. So which one of these would be a meso compound? It can't be both based off of the answers. Could anybody tell me? And it's not a trick. So remember, we're looking for a plane of symmetry. We're looking for a plane of symmetry through the compound. So for this one, it's going to be number 2. Okay? So if you imagine your eyeball, right? If you imagine your eyeball looking at number 2 this way, what you would see is this, right? You'd see something that looks like this, and you'd have a chlorine coming down and a chlorine coming down, right? So you can see the plane of symmetry is here. This is number 2. So this is a meso compound, right? Because this is a stereocenter and this is a stereocenter. But if you look at number 3, if you were to do the same kind of thing, what you would see is something like this, where you'd have 1 chlorine coming down and 1 chlorine coming up, okay? There's rotational symmetry here, but there's not reflectional symmetry. So this is not a meso compound. Does that help a little bit? I hope so. Okay, cool. Awesome. So the answer to that one is going to be number 2 is the only one. So remember, for meso, you got to have 2 stereocenters and plane of symmetry. The definition actually goes beyond that. It goes a little more than that. But for this class, this is what we saw in this class, is 2 stereocenters and a plane of symmetry. All right, let's try. I don't want to exhaust you guys with Kahn-Ingold pre-log rules, but let's just give this one a shot. Number 7 just asks us, what is the configuration of these 2 chiral centers, okay? And this is a Fisher projection. So you're going to see a lot of these in chapter 24 of Organic Chemistry 2. We'll do a whole chapter on carbohydrates. So this is a carbohydrate. This is called an aldotetrose, which is neither here nor there. But if we look at stereocenter number 2, the hydrogen is going to be lowest priority. The oxygen is going to be number 1. This carbon is attached to oxygen, 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 hydrogen. This one is attached to oxygen, carbon, hydrogen. So this is the tiebreaker. So now we can see that the aldehyde group is going to be number 2. Where is my pen? There we go. Number 2. Come on. Number 2. This will be number 3 here. So we're going from 1 to 2 to 3. So that's S. And so we reverse it because the hydrogen is coming out towards us. So it must be a 2R compound. There we go. And then if we figure out the chirality at carbon number 3, we have the hydroxyl is going to be 1. The proton is going to be 4. This carbon is attached to oxygen, carbon, hydrogen. And this carbon is attached to oxygen, hydrogen, hydrogen. So this is the tiebreaker. So we go 1, 2, 3. So we're going counterclockwise, which is S. So we reverse it, and it must be R. So it's 2R, 3R. Okay. For anybody who has the time, and I realize you're all very busy at this point in the semester, we have the final exam, coming up in a few days. But if you have time to go read chapter 24, I'm not going to go over it now because I'm not going to teach new content. But if you have time, you could go into chapter 24, and there's a section in there on stereochemistry of carbohydrates. And it gives it, if you can read through it, it will give you a shorter or a faster way of doing it. But again, the way that we learned in this class totally works, so you don't have to read that whatsoever, okay? It's not required one stinking bit. Okay, let's try, I don't know, let's try number 8. Hadn't planned on it. What's the relationship between these two compounds? So if you look at the first compound, you see that the hydroxyl and the methyl group are the two protons are trans to each other. So this is trans 2-methyl, this would be cyclopropanol, and this one here is trans 2-methyl cyclopropanol. So these two compounds are identical. They're the exact same compound. You call this trans 2-methyl. Now that you learned how to name an alcohol, you call this cyclopropanol. Okay, so if you have this compound, this is just called cyclopropanol. Anyhow, let's move on to number 9. This is more important. Is what would be the stereochemical classification of the product of this reaction? So we have this alkene, so this is 2-butene, and then we're treating it with HBr. And are we going to get the R enantiomer, S enantiomer, a meso compound, or a racemate? Well, I would say this. The final exam doesn't make you draw mechanisms, but I would say for this one, draw a mechanism. Okay, and it's going to help you greatly. So let's see if we can squeeze it on here. So it doesn't tell us whether this is cis or trans 2-butene. There's no information. Let's just draw it as trans 2-butene. It doesn't matter anyhow. If I add HBr, there's no Markovnikov and anti-Markovnikov don't apply in this case because both carbons of the double bond, they both have 1 hydrogen. So there's no, we'll put here, no anti-Mark, neither of them are anything to stress about here. So let's just draw a quick mechanism. So we do our proton transfer, and then we're going to end up with this. I'll draw it the way I have it there. Yeah. Yeah. Where am I? Here we go. So we'll draw the carbocation that's formed, okay? Then we have the bromide ion that's going to come in as a nucleophile. Is the nucleophile, the bromide in this case, is it going to discriminate between either side of the carbocation face? Or will it go to either? No, exactly, Jenny, right? So Jenny, could you answer the question? And I don't want to put you on the spot. But it's not just R and it's not just S. It's not a meso compound, right, Jenny? It's going to be a racemic mixture, right? She's absolutely right. So we're going to get a mixture of the R compound and the S compound, right? It's going to attack either face of the molecule with either likelihood, and the reason why is because a carbocation is trigonal what? Planar, right? So the nucleophile can come in on either face of the molecule. You see how they kind of ask, 2 or 3 things in the same question here, okay? You kind of have to think a little bit. Let's try number 10. Number 10 is a little more straightforward. Hey, could you guys answer this without any help from me or without me talking? These are all diastereomers, okay? There's no arguing that. They all have one hydroxyl, they all have one isopropyl and one methyl. Could anybody tell me which one of these would be the most stable one? And it's not a trick. There is no trick to this, just based off of what we learned. Is there one that looks more stable than the rest? Yeah, thanks, Raul. Thanks, Isaac. Yeah, it's B. Okay. The reason these guys said it's B is because, we'll just right here, everything. Let's put all. Let's be more scientific. All substituents equatorial, right? So you avoid, and you could say here, avoid all 1,3 diaxial interactions. That's it. Yep, everything's equatorial. See, as long as you know the concept, you can answer that question in a matter of seconds. And I don't mean to make light of the question because there's no simple concepts in organic chemistry. Before we take a break, let's try a couple more. I think that question 11 is a really good one. Again, this is in the same vein as the one we looked at a few minutes ago, but it's just asking you, will you end up with a meso compound, diastereomers, racemic? What kind of compound do you end up with here? So this is me not trying to fool you guys in any way, but for this reaction, would I have Markovnikov or anti-Markovnikov addition? And again, it's not a trick. Right, Jennifer? It's Markovnikov addition. And so I don't even need to draw a mechanism for this. You can if you want to, but it's going to be, like Jennifer said, it's Markovnikov addition. The rich are going to get richer, so you're going to end up with this compound. Now, is that a chiral compound? Is this a chiral compound? Yes or no? And it's not a trick. Okay? Same old stuff. It's right. Exactly, Isaac. A chiral. This is not a chiral compound, and it's not a meso compound either. The answer is it's achiral. It's not meso. It might be a weird way of putting it to you guys, but you can see it's clearly not diastereomers, right? It's definitely not that. It's not a meso compound. There's no chiral center in the molecule. And if there's no chiral center, well, it certainly can't be racemic. So again, it's not a trick or anything. It's just, if you know what Markovnikov addition is, you can see there's no chiral centers in the product, so it's not chiral. And it can't be a meso compound if it doesn't have achiral, but a meso compound is achiral, but it would at least have 2 or more chiral centers in it. Anyhow, also, question number 12, this isn't on your final exam, but I know that some of you have expressed interest in writing, the DAT or an MCAT or something, and this is a fair question for those. So I'll just tell you, this is not on your final, but I'll just share something quickly that you might remember if you're ever on one of those exams, is that when you're given Fisher projections, it's that you can't flip them over. You can only rotate them. Okay, so you can rotate, so you can take this and like spin it 180 degrees. Okay, and then if you were to rotate that molecule 180 degrees, what you'd end up with is something, and please don't let me screw this up, but anyhow, what you'd end up with is something that looks like this, a CH2, OH, and you have 1, 2, 3 chiral centers. So if you rotate it 180 degrees, these 2 hydroxyls are over here, and this one is over here. And then what you would do, okay, is you would compare this molecule with this molecule, and you'd say, well, what's the difference? Well, you can see that every single chiral center, this one is flipped, and this one is flipped. They're all flipped. So these are a pair of enantiomers. Okay, again, you won't be asked this on your exam, but for my students who are interested in writing the DAT or the MCAT, I would put here with Fisher projections, you can put here cannot flip like a pancake, only Rotate. Okay, you can spin them around. Okay, as if they were flat on a table, you can spin them around. Okay, but you can't flip them over. You can't compare them that way. Anyhow, but again, that question isn't on your, or something like that isn't on your final, so don't stress about that. Let's see here. Let's try a couple more. I like question number 20 because there's a lot of reading in it. Okay, so we just asked you to solve a little word problem here. Cyclohexene reacts with bromine to form 1,2-dibromocyclohexane. Molecules of this product would be. Well, if you were to write out what's going on here, you have cyclohexene, which is this molecule. You treat it with bromine, right? This is something we covered in chapter 8 in detail. You get bromination. Could anybody tell me, does this proceed with syn or anti-addition? The reaction that I'm writing out here. Is it syn addition, bromination, or anti-addition? Who remembers? Does anybody remember? Bromination, is it syn addition or anti-addition? Yeah, thanks, Jenny. It's anti-addition, right? So Jenny says we're going to get this compound, and then we're also going to get the enantiomer. So as long as you know that, then you can say racemic in form, most stable conformation would have both atoms equatorial. Well, if they're both equatorial, that would mean that they're cis, okay? Sorry, you guys. My iPad's good. So we'll put here, or sorry, no, both atoms equatorial. Sorry, I misread that. So if they're both equatorial, right, that would mean that you'd have the ring like this, but let's say you have this one down in equatorial, this one would be up in equatorial, and that would be trans, okay? So this is actually the correct answer. If you look at the other ones, one equatorial and one axial, well, that would mean that you'd have something like this where one is axial and one is equatorial. That would mean they're cis, so this is wrong. And then a meso compound, well, it's definitely not a meso compound, and then a meso compound. So a little bit of process of elimination for that one. Let's see here. Okay, I get another one for you guys. Then we'll take a break, okay? I know I keep saying break, and then I keep going because I like doing these. Hey, could you guys answer 21? What's the relationship between these? Are these identical? Are they conformational isomers, constitutional isomers, or stereoisomers? And again, there's no trick question. Could anybody answer this one? I'll give you a second to look at it. Okay, are these two compounds stereoisomers? Right? Raul, you got it. You're right. Right? It says here identical. Well, they're definitely not identical because this one is 1,2 and this one is 1,2,3. Right? So one is a 1,3 diol and one is a 1,2 diol. Right? A diol just means two alcohols in the same compound. So they're definitely not identical. They're not conformational isomers because conformation would be just flipping the ring. They're not stereoisomers. They're not even connected in the same way. Like Raul said, they're just constitutional isomers. They just happen to have the same molecular formula. That's all. That's the only thing they have in common because they're not connected in the same way whatsoever. Great. Okay, so what we're going to do is we're going to take a break. But if you want to, you could try to solve this one because this is the one I wanted to look at next. Because I feel like this one involves a little bit of work. Okay, is figuring out which one of these reactions is going to give a meso compound. And then when you see D2, so D2, it's similar to H2. It's just you put deuteriums in. And remember, deuterium is hydrogen 2. Okay, it's hydrogen with one neutron in the nucleus. Anyhow, so we'll come back and we'll do that one. I was just looking at this one. What's this one? Would form a racemic mixture. Anyhow, I'm getting ahead of myself, but yeah, let's come back and we'll take a look at question 25 after the break.